The next speaker is Professor Robert Dibble, who is a professor at CCRC. He got his PhD in chemical engineering from University of Wisconsin in 1975, and after a postdoctoral fellowship at Imperial College London, he joined the combustion research facility at Sandia National Lab. In 1990, he then joined the mechanical engineering department at Berkeley, where he stayed until 2014, when he joined the CCRC. So he's a recognized expert in gas turbines, spark-ignited, and diesel engines. And in fact, his talk will be a review about Otto and Brayton Cycles using Argon as a working fluid. Thank you.
Thank you very much. The title here is a bit different than what's in your paper, because what I submitted to the secretary, she said it's too long, so I gave her one that's short, but I kept the real title, okay? The introduction's almost right. I actually retired from UC Berkeley in 2013, in large part because I had several options to start companies. And if you live in the Bay Area, you view yourself as an entrepreneur and want to start something. And here, Bill Roberts made me an offer I couldn't refuse, because I basically get to start my company, which I'm about to show you. Something that I'm working on and passionate about, and you'll see all about that. Secondly, just advise you all that I have a textbook, and Jürgen Varnatz advised me and warned me that when you write a book, then every time you look at some other talk, you keep asking yourself, should this go into the book? Is this valuable? Should we change our book? Are we wrong? And so on. So I'd like to thank everybody at this conference it's caused me great concern about the book here. That is, there's many good things that we saw in the last few days, and so I have this list of things that I have to go back and start picking through some of the stuff and say, how do I work this into the textbook to make the textbook more relevant? And all of us who are teaching know that textbooks are usually 20 years out of date, okay? It's just, they can't keep up, and it's very hard to keep up. This shirt is quite a collector's item, because it played really well in Livermore High School, because this is about the 4th edition, and here at KAUST I will finish the 5th edition. So this book, you want to burn the old book, right? And students at Livermore High School were wearing this shirt, and they really loved it, and I got a call from the high school principal, would I stop it, okay? So anyway, that shirt says, burn this book, it's a collector's item. So let's get started. I tell my students that when you start a talk, you should kind of get people oriented where you're from, and so I always had something like this, and let's see if this laser is going to work for me, maybe, yeah, there. And there's the Golden Gate Bridge, and on a clear day you can see China. But I've, as I think everybody here should know, that I've moved, okay, and we're all here, and I wanted to I'm looking for some kind of, this is the best I could grab at short notice to sort of start to introduce, well, where are we? And as I said here, we're right in the middle of everything, because we saw Perth earlier, it's over here, and Berkeley is over here. Now, amazingly, I was lucky enough to fly back to Berkeley one of these days, and I'll fly back actually Saturday morning like everybody else. But I have a nonstop to Los Angeles, and amazingly, it goes this way and comes down here to Los Angeles. You'd think we're going to go like this, right? But no, you go up and come back here. So these maps aren't what they seem. It does remind me that Saudi Arabia, to cross from here to there, is a 2-hour flight on a jet airplane, and 2 hours from San Francisco puts you sort of in Denver. So this part's accurate, that is the width there and over to Denver, about the same. Although here it seems like these countries are too small right now. I said, so I don't know about that map. Anyway, so much for our introduction. This is where we are now, right? Somebody told me, he says, oh, Dibble, you're going to give the same talk again, you know? And I go, yeah, somehow I always change it because I think I did it wrong the last time. So here, I start out with the engine, okay? Because I've been accused that this will never fit into a car. And I said it never intended to be fit into a car. So I start out with, this is the kind of engine we're sort of talking about, okay? So with these big engines, and here's a crankshaft, right? That's the crankshaft to that engine. And here is a person kind of bent over doing I don't know what, but he's got a blue hat. See that little blue hat? And kind of get the scale size of this, and this is a 100 megawatt engine, okay? The next picture is, we saw several pictures of turbines, but it's hard to put it in scale, and I've been trying to come up with a metric, and all I can tell you is there's another hard hat, okay? So the hard hat in this picture is you know, this engine here might be 20 hard hats in length, whereas the other engine was like 100 hard hats in length. And that's kind of the deal, is why do you go to a gas turbine anyway? And it's because ultimately the power density of a gas turbine is higher. And so this is a 200 megawatt turbine, and it's definitely smaller than the piece of iron. This does go backwards. So it's definitely smaller than this thing right here. Which one costs less money? I don't know. I suspect this one, even though it's got a lot more iron, it's only iron. There's a lot of high-tech metals and stuff back in this part here. We've seen some people talk and saying engines are upwards of the up at 60 some odd %. Well, that's when you get to 50 to 100 and more megawatts, you can have efficiencies up in this area. Here we're showing gas turbines. Maybe this curve's a little bit low because with the combined cycle, having both gas turbines and steam, it'll bump you up to like 61 is what both Siemens and GE are now touting. So we say that you can get a 50 to 57% efficient diesel engine now, and so we'll talk about that in a minute. It turns out, why is that? Why do these big engines get better and better? It's because the heat losses goes d squared and the energy inside the piston is d cubed, so you get more and more approaching the adiabatic. And that's the primary reason that big engines are more efficient than small engines. Never mind that, okay? There's many cities that power themselves on these kind of piston engines. In particular, I can think, I've been to Costa Rica, and the city of San Jose, Costa Rica has 16 of these engines to make the lights of that part of Costa Rica. Here's just another example. And so we claim that, you'll see why, we claim that we're going to make a 75% efficient engine, okay? And we start out with saying we're going to swap the working fluid with argon. It says here we're going to put oxygen into here, port inject oxygen, and we'll direct inject the fuel hydrogen. I do that to get everyone comfortable, but if you look at this quite a bit, and you'll see two things. One is we'll most likely port inject the hydrogen and direct inject the oxygen just because this has so much more mass than that. Second of all, we'll probably coaxially inject both of these things. More of that in a minute. There's our engine again. So this is you're taught in thermodynamics about the Otto cycle, and you should be sort of an undergraduate exercise derive this equation for the Otto cycle efficiency. It's compression ratio raised to the gamma minus 1. And sort of what started me on this is we see that as we're in the engine community, because of climate change, and not because of the high, quote, high price of fuel's cheap, because of climate change, there's legislation that everyone's required to get less CO2, which means more efficient. Excuse me. So less CO2, more efficient, and so everything's being changed on an engine. If you own an American V8, keep it. It'll be a collector's item. Engines are downsized. BMW has announced their 3-cylinder engine for their large car. It has 3 cylinders, 2 stacked turbochargers, and can boost to 4 bar. naively, 4 bar times 3 cylinders means it's actually 12 cylinders when it is going to full power. So, you know, these are the various things people are doing. They're also going to 10-speed transmissions. That'll be routine on cars, if not already. So I said, well, look, if you're going to do all these things, tweaking engines, changing the valves, making Miller cycles, all these buzzwords, why don't you step back and let's talk about changing the basic thing that we consume air. And instead, if we use argon, then we can jump from these curves to these curves for the same engine. Even some people, you'll see a quote from a VP at a large engine company said, yeah, Dibble, that's a quantum jump. Really it is, okay? So we're talking about switching to argon as a working fluid, and the easiest thing to think about is we'll start by burning hydrogen and oxygen. We'll talk about that, but this will grow. It'll take a few years, but you know, we'll start talking about someday how would you burn gasoline and still use argon as the working fluid. I don't have an answer to that right now, but you know, I think it'll grow. So this is the basis of the talk, is really, we're going to jump from here to there. We see that it does do wonderful things. That is, it'll increase your efficiency by a factor of this ratio, which is about 1.4. So if you take those engines that I showed you at the front end that are like 60%, well then I'm going to improve their efficiency by 1.4. And we have data already to prove that, okay? So here we go. The first application that we really, started to really get our imagination was the growing field of energy storage. And I didn't believe it, but it turns out the Argon engine looks like a contender for storing excess energy. And we'll see a little bit more of that. Later we think, well, we think we could be on boats and maybe locomotives, you know, still pretty big. And of course, always electrical generation. We think you'll see, we could talk about maybe coal and natural gas. How would we work that in an Argon cycle? Sidebar a little bit, there's something that's, again, energy storage is new, really didn't exist 10 years ago. So talk to venture capital people in the Bay Area. This is one of the most exciting areas in business now, is the energy storage business. Because we're committed to renewable energy, that being solar and wind and others, we are confronted with what somebody calls a duck curve, and I apologize that when it's in black and white, it looks like a duck. Here's the head, and then back here's the tail. But now that it's been colored and decorated, it doesn't quite look like a duck. But trust me, if somebody ever mentions the duck curve, this is what they're talking about, and that is that you have excess energy during the daytime, and you want to store it and divert it, excess in the daytime and divert it and give it back at nighttime. I thought that energy storage was something on the order of hours, but many people are talking about days. So if you're really serious about talking about days, flywheels, they won't work, and there's other things that will come up. Right now, my biggest contender really is batteries, and we'll talk more about that in a minute. I guess a special note right here. In Berkeley, there's a startup company that does compressed air storage, and they're contenders. But we had a discussion with them. They come to our conferences, and if you compress air, we say that you will need at least 50 times more tanks to store your air than I need to store hydrogen and oxygen. And so we laughed and to the compressed air people, and they said, if tanks are expensive, I win. If tanks are cheap, maybe you win. And not only did they agree with me, but they finally confessed that they have kind of evolved, and they're in the tank manufacturing business. Okay, so I'm going to be one of their customers, all right? What an evolution out there. Okay, so I guess I've already said this. Renewable energy, you know, wind power peaks at night, didn't know that. Waves are sporadic, and solar power intermittent. And I love my computer that can do that, right? So energy storage is the lucrative answer, and I said I'm going to form a company called Buy Low, Sell High, okay? So I guess I decided somewhere in the talk I'll give you an outline. So right now I'm talking about using the Argon power cycle for energy storage, and we'll keep going. So if you're going to store energy, I have colleagues at Berkeley that are in flywheels. And to my amazement, I thought a flywheel would spin up, it would stay there for 12 hours, and then you'd spin it down, and that doesn't happen. Actually, the characteristic time of a flywheel, try as you may, is typically less than 1 hour. Water pump storage is unquestionably the best way to store energy. So all you need is a large lake, say 1,000 meters above where you are. And here in Saudi Arabia, that's going to be difficult. And in fact, many parts of the world, just not possible. Where it is possible, it's being done. So, you know, water pump storage is good, no question about it. Compressed air storage, pending, let me say pending, and batteries are most popular so far. And right down the street from us in Berkeley is Tesla Motors, and we know that they're working very hard on getting the lithium-ion battery price down, down, down. And I have to say, if you look at, and they tell me that they are my strongest competitors against the Argon cycle, so we'll see. Okay, well, you'll see my whipping boy here is a fuel cell. You got to create a two-horse race, and so it's me versus the fuel cell. And I call them a fuel cell, and it's just my observation, okay? So what am I going to say? So, you know, we're going to have excess electricity, and you store that energy by generating hydrogen and oxygen. Okay, later we're going to burn the hydrogen and oxygen in a fuel cell, or else you can come over to me and we're going to burn it in the Argon power cycle. And I argue, and I'm pretty clear on this, that we're at least as efficient and it's far less complicated. Okay, what do I have to do? Well, my exhaust only has water and argon. I remove the water by condensation, and then I just recycle the argon to the intake, and we've said that before, okay? I had to put this in here. A lot of people talk about EGR on their engines, and I laugh. This is 100% EGR, and that'll come up again in this talk. That's kind of interesting. Fuel cells are typically this price, $5,000 a kilowatt, and piston engines are less than $500 a kilowatt. So 100 megawatts of power will cost $500 million in fuel cells, or less than $50 million in this kind of hardware. And this is what we're talking about. And by the way, by legislation, the companies, power companies in California, for sure, and elsewhere, are required to have about 1/3 of their capacity in storage. They've got, by law, that's required. So they are going to buy stuff, and the requirement is they start to place the order by the year 2020, with the idea it'll be installed by the year 24. And so everyone is scrambling, myself included, to be somewhere by 2020 where they would consider buying an Argon engine as opposed to batteries. So once again, I say it's simple. Of course, it starts out that way. The devil is in the details, and we'll see that in time. Yep, okay, we've been there. So I did some experiments early on with spark-ignited engine at Berkeley, and I started in 2009. And the idea was we had the engine running on air and hydrogen for 5 minutes, and then a single-cylinder engine. Then we switched the input to pre-mixed oxygen in argon and port fuel injected hydrogen, spark, and we had a runtime of 10 seconds. Like the previous speaker, Farouk, professor, no, the previous, I did my PhD on a shock tube, and so I'm inclined to always do short burst experiments, and so this is just one of those examples. And so we did that, and I should have known what's going to happen. Surprise, the engine knocks, okay? Why did the engine knock? Right out of the gate. The minute I switched on the argon, it started to clatter, okay? It was a CFR engine, so it's designed to take knock, and it did. Well, here's the reason. Is when you compress air, you raise it to this temperature here, but if you compress argon in the same thing, it gets way hotter, and therefore it was hot enough that all these fuels would auto-ignite well before top dead center. In fact, I was having an engine knock at a compression ratio of 5, which is kind of unheard of. This is another picture showing if I start at 400 intake temperature, well then the compression ratio can easily take you to way hot, 2400 Kelvin, okay? That's more of the same. Why is that? Thanks to graduate student Tim Sonnet, here we have a little cartoon showing you that, like, triatomic molecules have several degrees of freedom, but argon itself only has translation. So as the piston moves and compresses the gas, it is exciting all these degrees of freedom in diatomics and triatomics, and that absorbs a lot of energy, but argon doesn't have these degrees of freedom, so it can only absorb the energy as translation, so it gets way hotter. But on the same breath, this is the most efficient extraction of work, is when you work with a monatomic gas. Thanks to Tim. There it goes. Okay. Here's some, we have software also, not large eddy simulations or anything. We have sort of a much higher level, some software made by ABL is called Boost to model engines, and other software widely popular is called GT Power. Anyway, they're kind of like 1 or 0-dimensional models. But here I'm compressing gases, and I think on this one I made a point of trying to get to the same starting temperature, and then if you add the same amount of fuel, the argon jumps up much higher temperature than air. For the same reason, it's a monoatomic. So when you deposit a certain chemical energy into argon, it gets hotter than the comparable into air. Of course, all of us have been in combustion, know that immediately that this will produce more NOx. But there's no nitrogen in this system, okay? So it doesn't produce more NOx. But you worry, wait a minute, it's getting hot, so therefore let's look at heat transfer. And so these codes do look at heat transfer. And yes, there is more heat transfer. So we worry about that and look at the main code here, which does the whole cycle. And here it's showing the work as a crank angle, and indeed compressing argon requires more work, but then it gets more work back out. So, and this model here includes the heat transfer. So the heat transfer, although it's higher, we're still getting more efficiency out of this whole cycle. One last comment was, with higher temperatures, we have higher pressures, and this ratio of temperatures here suggests that we will certainly be above 100 bar in this engine routinely. And so this is a high pressure, high Reynolds workshop. Certainly we're going to be at high pressures. Let's see if we're going to be at high Reynolds number. I think I told you earlier that as these engines get larger in diameter, here's a calculation, we increase the bore diameter, and you can see increasingly we're approaching the adiabatic limit. So we're trying to be around here for much of our research. Never mind that one. One last thing, these models are great. If you start throttling back, that is, I say I'm going to slow down and inject less hydrogen and less, finally you get to the point where your efficiency drops tremendously, and it's because finally you do not have enough power in this engine to overcome friction. So I'm trying to show you that this model has lots of fidelity in it. It includes friction and many other things that happen inside of an engine. So this is correct. Okay, so I told you my SI engine, I was set back by knock. So we said we're going to convert to a diesel mode, go from spark ignited to DI, direct injected. And we suggested we would port fuel inject the hydrogen and direct inject a liquid, maybe oxygen, but we could, just to get going, use N2O, and we could use H2O2. So those are just options we're looking at now. We did have a meeting just before the, where was that at? First meeting was 2nd of August, just the Saturday before the International Combustion Symposium in San Francisco. And a lot of people were at that meeting. And basically, I was eager to be there. What I wanted to come out of this meeting was, did we pass the laugh test? I mean, is this a curiosity or is this a real idea? And we did pass the laugh test. And see, I have a star. I don't know how to make that red, but I want it to be red because I've been teaching with China for 5 years, and particularly at Tongji University. And so Tongji has embraced this cycle also, and we made a joint proposal to the China NSF and to the USA NSF, because they were encouraging a joint program between China and the United States, and so that's pending, okay? So So an Argon cycle working with China, Tongji University, and with Berkeley, and then of course now going to be KAUST. Here I do a calculation for you. I was astonished to find out that a electrolyzer that makes hydrogen and oxygen from water is only 75% efficient. And that's a fact. And Siemens makes one now, 5 megawatts, and they're under construction is a 10 megawatt unit. They think there's a market growing for these. So there is definitely a market for stored energy with electrolysis, and they confirmed that, yeah, that number's like 75%. So fuel cells, when they're delivering power, are, you know, seldom more than 50%. So the round trip efficiency is 37%. And so you put in 100 units of energy, you will get 37 units returned to you. On my side, because I'm 75% efficient, I have the same 75% efficiency for electrolysis times 75% for the engine, so I get 50% for the round trip, which I didn't think was very good, but then people in energy storage said that is good. And they said it's competitive, it's not the very best. The batteries can be as high as 80% for this number, but they said those batteries will cost 10 times more than my system, and all these systems are going to cost on the order of $1 billion. So the difference between $1 billion and $10 billion is what's going to be on the table. So here I am selling you the Argon engine. It's more efficient, it's less complicated, and lower cost. So, okay, this is just all metal, and you're all sitting there going, yeah, what's new, and why are we here? Remember, this is KAUST, and the T in KAUST is technology. So much of what's doing here is the science part of KAUST. I'd have to say I'm carrying the technology banner at KAUST. So I say it's not rocket science, or is it? And oh, it didn't bounce, okay. We had a talk earlier this week, and I asked Benedict if she could loan me her slides, and this is what she did. She was showing hydrogen mixing with oxygen, and here she is at the critical point, right along that area right there, supercritical fluids. I'm not quite there because she was at, what, 150 Kelvin. I'm going to be up here at 300 Kelvin, so in a way, I will not need the Pang-Robinson equation. But because as I was introduced, my PhD and undergraduate degree is in chemical engineering, so I actually know what a Pang-Robinson equation is, okay? And I'll bet the rest of you don't, okay? So I'm going to just move along here, and she had multiple jets. I might have to consider that also because hydrogen's going to have trouble mixing into this Argon chamber. I talked to Professor Bassetti about this, and while I was talking, he Googled rocket motors, and he said rocket motors always have the oxygen in the center core and the hydrogen surrounding it, so end of story. And so no doubt when I do injection on this Argon engine, the oxygen should be in the center. And here is really interesting what I wanted to show you all, and I was sitting on the edge of my chair as she presented her stuff. Here's hydrogen, and it looks like a lot's going on. It looks like it, but look at the oxygen. It's doing almost nothing. It is so massive compared to that the oxygen is blowing in like that, and we've got not anything like the oxygen truly mixing. So, you know, well, more on that. She's got a close-up here. Once again, look at the oxygen down here. It's not doing much, really. We got a lot of activity, maybe recirculation and things, hydrogen doing all kinds of things, but truly, there's not much going on. It's going to, I don't know what's going to happen, okay? So it turns out we are asking ARPA for $11 million. That's the size of this program. I mean, that's what it, and in the Bay Area, a venture capitalist will ask you, what keeps you awake at night? You know, if you're asking for $11 million, they say, what keeps you awake at night? Well, what keeps me awake at night is the last pictures you saw. So the mixing of hydrogen and oxygen into argon at 100 bar. I don't really know what that's going to look like. And trust me, everyone's vision of how fluid gets injected into another fluid is prejudiced by the fact that the fluid you're injecting is heavy. And typically it's liquid fuel. You know, so this is a case where the fuel, the thing you're injecting is very light. So it's going to be different. And of course, at 100 bar, it's going to be different times 100. The other thing is, I don't worry so much about the engines themselves, but I have a requirement that I have to recycle the argon, and I need to remove all these things from the exhaust. So that actually keeps me awake also, and I don't think anyone here has to worry about that, but I have to, okay? And let's see. By the way, not everyone knows that argon is 1% of the air, and it's affordable. It's actually a byproduct of making liquid air. So don't worry. And also don't worry, as one person did, could I possibly be so successful that I would tap the world's supply of argon? I wish, okay? Okay. Okay. I've told you, the energy storage is the fastest growing sector of power gen, and in venture capital type things, they always want to charge into a growing market. They really never want to attack an existing market. Okay, we did that, okay. Vice president of a big engine company told me this stuff right here. He says, this all looks entirely workable. There are no insurmountable barriers. We will build it when there's a market. So he just says, you know, when it's time, we'll build this thing. And so the good news is, it's coming. But right here now, part 2 of my talk is, just discovered that there's interest in the argon power cycle for enhanced oil recovery. We generate hydrogen from reforming, and Cal Gotke had to leave, but he has his pet term is over at the Aramco side of the peninsula, is he at the refinery has many homeless hydrocarbons. Hydrocarbons that they, don't know what to do with. And so one thing that you would do with the homeless hydrocarbons, which actually includes methane, is you'd reform it to make hydrogen, and then the CO2 we're going to pump down hole to recover, enhanced oil recovery, and we're going to have to get oxygen from a air separation unit or distillation. I was advised last night that right there will cost me 15% of my efficiency, but be that as, okay, that's all good because, this looks interesting. So, as I said, the vice president told me we'll build it when we have a market. Well, now I think we have a market. So we're back to this engine again. Now it's going to get modified that the oxygen is going to come from a air separation unit or distillation, which also, the distillation makes argon. That's a deal. Hydrogen from a reformer. And then we're going to compress the CO2 for enhanced oil recovery. It seems like this goes like that. And then I have to remove not only water, but I got to remove CO2 down in this part right here and nitrogen. And that keeps me awake at night because nitrogen and argon are very similar looking molecules. So separating nitrogen from argon, don't know how to do that. Last is another cycle variant. And so this one here is radical because, for me, because there's no argon at all. So I'm abandoning the argon and just looking at, and this is not radically new, but nonetheless, I was asked to consider this by the previous customer, and that is, and we have worked on this, Professor Chen at Berkeley computed with 30% oxygen and 55% CO2 with 15% methane, the laminar flame speed of this mixture is the same as stoichiometric methane in air. So we have to go to that much oxygen to get this thing to have the same flame speed. What else? Okay, so then we're going to take the CO2 is going to have to be just diverted from this exhaust. And so some of it's recycled, something like this, and the rest of it is going to be for enhanced oil recovery, okay? So yeah, 90% of the exhaust is going to be CO2, 90% CO2 exhaust will be sent downhole for advanced oil recovery. Okay, so that's the main 3 things I'm working on, but I was asked, please consider gas turbine. And I've always told people, gas turbine's more trouble to me because I worry about the efficiency of compressing through all those blades that were designed for air. How will it work for argon? I don't have these problems with a piston engine. This is the Brayton cycle, so, and we've now modified the way I want it, so I'll bring hydrogen, oxygen, combustion chamber through an expansion turbine, collect the argon and water, take the water out, and then recompress the argon. It'll be that loop right there. The similar arguments apply. When you put in argon, you jump from these curves to these curves. The equation here is slightly different, and so the bump up factor is for the piston engine, it's a pretty steady 1.4. Here it's 1.2 to 1.5 depending where you are. And if you're way out here, the bump up is more like 1.3 or something. Let's see what I say. They're called Brayton cycles. Brayton wrote his patent before there were turbines. And so Brayton's patent back in the 1800s is all about pistons engines. So he had piston engines for compressors, then he took it off the machine, had a combustion chamber, then back onto a piston machine for the expansion. Turbines didn't exist. Anyway, 40 years ago, a nuclear reactor operated in Colorado, and not on a steam cycle, or a Rankine cycle, but instead on a closed Brayton cycle, and it used, where's my stuff here? Helium. And so that's good enough, but I'm using argon, and I thought, why would you use helium and not argon? And you might think better heat transfer, but we don't want heat transfer, so maybe we better have argon. And I checked why, and I had to ask around quite a bit, and finally I got the answer. It's here. The argon became radioactive inside of the nucleus. So argon weighs 40. It has a substantial nucleus, and it would absorb. It became radioactive. That's all I could say. Okay. So now, I think I told you that you can get this kind of power in a lot smaller package with a gas turbine. Okay, and we had these pictures before. So here I am talking about work in progress. Will a gas turbine designed for air 29 be okay with argon 40? And the short answer from an expert is no problem. And he went through 8 different steps. And I'm sparing you that. But he said it'll be 10% higher here, 10% lower there, 5%, 12%, and so on. And he said when you add it all up, it looks like it's going to be okay. We need to dig into that a lot more carefully. I asked him the same thing, let's see, about CO2, and he was more hesitant. He said, no problem, but really need a closer look. Okay, so we're getting close to the end here. A special note, I was excited when, in the Q&A, a banker raised his hand, and the banker who has invested in batteries for energy storage, and his company is called Megawatt Storage Farms. Nice name, okay. He said, when the storage of hydrogen and oxygen is exhausted, the argon power cycle can rapidly evolve into an air-breathing engine burning natural gas or other emergency fuels such as dimethyl ether, liquefied petroleum gases, or methanol. And to the banker, he said, that's really the most important feature of your device, which I hadn't even thought of, and that is that he said, even after you've exhausted the storage, he said, you do not have which is a hard word for a banker, a non-performing asset. Okay, this is really important to a banker. So this device then it was well appreciated by the banker for this reason here, that it continues to work. Now this is kind of interesting for everybody. You're in combustion. For every engine in this talk, there is no exhaust at all. And so now we have arrived at a time in the history of combustion where we've tolerated smoke in the 1800s. In fact, it was a sign of prosperity, a big smokestack. The village was doing good. We're making money. Then we quit doing the smoke, and by say 1960, we could see that the automobile was polluting our air. So we start seriously with, say, the three-way catalyst and other measures to clear the air, certainly by 1975. And I think we are heading towards an era where there will be no exhaust, which is hard to grasp, isn't it? And so the first time you heard about climate change, you probably said, I don't believe it. Okay, so let me say that this is the first time you heard about engines that have no exhaust at all. And I think we're headed there. I am, matter of fact, flying back to California on Saturday, and you saw the trajectory I was going to fly. And I'm meeting with people from Norway who are very excited about engines that have no exhaust. So we'll see where that goes. I put this picture from Tim just to remind us that we certainly think that ships like this are something that we could be dealing with. This is a review of what I talked about, and I'm here. Okay, thank you.